All right, in this video, I'm going to go over discussion activity Gauss's law. Now, I'm going to skip over the pre-activity sheet, and we'll talk more about this at the end. All right, so the first question here asks us to hold a small piece of paper flat in front of us. And this paper can be thought of as a larger planar surface. We want to figure out what single line could you use to specify the orientation of the plane of paper. So here I have a little piece of paper here. I see that I can change the direction of this plane of paper, and in order to specify the orientation, you might think, well, maybe I can, if I imagine this pencil as being my vector, points along some direction on the plane. But remember, that's not enough information, because without changing the vector, I can change the orientation of the paper. So what's better is if instead I imagine a vector that is perpendicular to the plane of the surface. So now, as I move the plane around, I can still specify the orientation. So what single line? A line perpendicular to the surface. Now, what does that line represent? The direction of that vector? Well, that will tell me something about the orientation of that area. And the magnitude is going to be that total area. So total area, and here the direction will represent the direction of perpendicular to surface. Now here, if I imagine taking a sheet of graph paper, right here I have a sheet of graph paper. Now what I can imagine is, well, what does it matter about the little pieces that make up that area? Now, for a flat sheet, the total area vector and a little piece of that area vector, what I might call dA, are going to have the same orientation of their area vectors. And what will be different is the magnitude, right? The little dA area will be smaller. So the direction and magnitude of the area vector for the entire sheet of paper would point perpendicular to the paper and have magnitude equal to the total area. Whereas for the little area vectors, the little dA vectors, each individual square will have the same orientation, but its area will be one small part. So next, I want to lightly fold the graph paper so that I end up with a hollow triangular tube. So here I have my tube. Now, I wouldn't be able to describe the area vector of this entire tube with just one vector, because each of these sides has a different perpendicular direction. And so I'm going to need 3 area vectors. Now, it's certainly true that each one of the squares that will make up one of those 3 sides, just similar with the graph paper that was flat and the little dAs that made it up, all of these will share the same orientation for their area vector, but they'll have the smaller area. Now, if I unfold the paper and roll it up into a tube, I see that now there isn't really a finite number of directions that specify the area vector now. And so I won't be able to represent it in the same way as I did in question 3 or in question 4. However, I can still imagine there being a whole bunch of little tiny squares that each has its own area vector, dA. And so what must be true about a surface or a portion of a surface? It must be what we would say locally flat. In other words, if I zoom in close enough, if I make my area tiny enough, that it will appear to be flat. All right, so next we have a little section here about the electric field and the field line representation of the electric field. The field line representation will let us think about Gauss's law in a more straightforward way. So here I have a positively charged rod, and I have the electric field lines that are drawn. I have two different positions, A and B. Now, in a previous activity, we showed that at A and B, that the electric field is stronger at A than it is at B. And so what feature of the electric field lines reflects that information? Well, it's going to be how close together the electric field lines are at a position. Notice how the electric field lines are closer together near region A than they are in region B. And so what we'd say is the density of the field lines is proportional to field strength. Remember, this is just a representation. I could put double the lines here, but that doesn't necessarily mean it would be double the strength. It would all depend on sort of what I said was going to be the conversion factor between field line density and electric field. So now we have the field line representation of a uniform electric field. Now, the key here for our uniform electric field is that the electric field at each of these positions are equal. So the electric field, both in magnitude and direction at P, is equal to the electric field, both in magnitude and direction at Q. It doesn't matter that P isn't directly on a field line. Remember, this is just a representation of the electric field using the electric field line representation. Now, if I wanted to draw another uniform electric field that is weaker, I go back to my answer for 7, and I would change the density of the field lines. Here I would say by removing the line, so perhaps I could do something like this. I could have electric field lines like so. So the electric field here is weaker than the electric field over here by changing the density. So when I draw, I would decrease the density. All right, so now I want to consider a square loop of side A. So a square loop of side A would look something like this if I were sort of looking down the center of that square loop. And instead what I want to do is I'm going to draw an edge on. So I'd have one that looked like this and one that looked like this. So this is just the loop rotated. Now I want to draw a diagram to show the relative orientation of the loop and the electric field so that the number of field lines that pass through the loop is a maximum possible and a minimum possible. So if I draw my electric field lines like so, here I have the maximum number that would pass through. And here I'd have the minimum number that would pass through the loop, right? And so this quantity, sort of the number of field lines that pass through an area, is what we're going to call the electric flux. And so when we're at our maximum, it is just the area of the loop times the electric field at that surface. And if it is in this orientation, then we'll just say that it's 0. Now we can also have positive electric flux and negative electric flux. Positive electric flux is when the E and A vectors are in the same direction, and negative is when they're in opposite directions. So let's sketch out each of those 3 situations. So again, I can draw the area vector, and I can draw the electric field vector. This would be a positive flux. If I have the area vector like so, and the electric field in the opposite direction, that'll be negative flux. And if the area and the electric field are perpendicular, then we would have 0 flux. Now you might be able to recognize what formula would tell us how to compare the angles between the area and the electric field to get this behavior. And it turns out that the flux is equal to the magnitude of the electric field times the magnitude of the area times the cosine of the angle between them. So when the angle between them is 0, cosine is 1, we get our maximum value. When the angle between them is 180, cosine of 180 degrees gives us -1, we get our negative value. And when the angle between them is 90, cosine of 90 is 0. And so we get 0 flux. So now we want to actually try and apply Gauss's law. Now here we have a description of what Gauss's law is. Now Gauss's law says if you add up all of the flux on each point of a closed surface, that will be equal to the charge enclosed. So what do we mean by a closed surface? That's what these next activities will have us think about. Well, we're going to choose by convention that the area vector points out of the enclosed region. A enclosed region is a region where in order to get out of that region, you would have to pass through that surface. So we're going to consider a bunch of cylinders, and we're going to figure out the sign and the magnitude of the flux. And for the magnitude, we're just sort of going to speak relatively. We're not going to actually calculate out what that value is. So to start, we have a uniform electric field that is aligned with the cylinder. The top surface is A, the side surface is B, and the bottom surface is C. So the first thing we want to figure out is what is the direction of the area vectors. The direction of the area vector for surface A, so I'm going to have the area vectors for each of these, and we're going to figure out what direction they point. So for surface A, it points up, and for surface C, it points down. Now for surface B, it sort of depends on what side we're on. So for example, if we're on the left side of surface B, it points to the left. If we're on the right side of surface B, it points to the right. If we were sort of between the paper and us, it would point out. And if you were behind the cylinder, it would point to the back. Now next, we want to figure out what direction does the electric field point. Well, the electric field starts from the bottom and points up. So for A, at surface A, it points up. For surface B, it points up. And for surface C, it points up. Remember, it's a uniform electric field. So if I figure out the flux for surface A, I'd get a positive number. And if I figure out the flux for surface B, I get 0. And if I figure out the flux for surface C, I get negative. Now, how do these two magnitudes compare? Well, I know the strength of the electric field is equal at A and C. And I know that the areas A and C are equal. The area of A is equal to the area of C, and the electric field at A is equal to the electric field at C. In other words, the magnitude of the flux on the surfaces is equal and opposite, such that when I add them together, I get 0 flux through this entire surface. Next, we're going to, instead of having a uniform electric field, now I'm going to have a negative charge located at the center of the cylinder. Now, the areas are going to be exactly the same, right? Just because we've changed the charge and electric field doesn't mean we're going to change the areas. So it's going to look something like this. Now, the next thing I want to do is I want to draw some electric field lines so I can get a sense of what the electric field looks like at each of these surfaces. So I'm going to draw some representative lines. Now I know that the electric field lines for a point charge point radially inwards. And since this is a negatively charged charge, they're going to point towards the center. So what direction does the electric field point at surface A? Well, it points down. what direction does the electric field point at surface B? Well, on the left side, it points inwards, and on the right side, it also points inwards, so it points to the left on the right, and on the right on the left. And for C, I see that it points up. Now, when I compare the area in the electric field following our rule for positive, negative, and 0, I see that I get negative at A, negative at B, and negative at C. Now, I can also say that the flux at A and C are going to be equal to each other because of the symmetry. Same area, same strength of the electric field. Even though it's changing over the surface in strength and in direction, it's doing it the same way at surface C. And right now, I can't definitively say how exactly how the magnitude at B compares to A and C. But my guess is it's probably a little bit stronger. It's a larger area and it's a little bit closer. But at the end of the day, I add all three together and I get a negative quantity. All right, next up, I have two charges that are located inside of my cylinder. Now, my surface A, B, and C area vectors are all still the same. And again, what will my electric field look like? Well, I know that sort of for my dipole situation, it sort of looks like this. So I have sort of one like that, pointed radially outwards. Here I have one pointed radially inwards. And I get something that on the side, there's one that points from the positive to the negative, and it will curl out like so. This is what my dipole field looks like. And again, the arrows point from the positive to the negative. Something like this. All right, so let's look at surface A. Well, it looks to me like surface A, the electric field is pointed up. And at surface C, the electric field is also pointed up. Now, if I look at surface B, let's imagine I sort of split surface B in half. See, on the top half of B, the electric field, so the top of surface B, the electric field is pointed out, so to the left or to the right. But at the bottom of surface B, I see it's pointed inwards, so in on both sides. Now let's figure out what the flux is here. Let's see, for A and E, they're in the same direction, so that's going to be positive. Let's see, A and E are in opposite directions, so that's going to be negative. Now, what about the flux through surface B? Well, in the top half, we'd have positive, and in the bottom half, we'd have negative. And again, due to the symmetry of the charges and where they're located, we expect these to perfectly cancel each other out. Because for every electric field line that comes out, that same electric field line comes back in. Likewise, by symmetry, I expect that the magnitude at A and C should be equal due to the symmetry of the cylinder. And so that the net flux should give me 0. And finally, let's go to question 4. Again, I'm going to draw, well, first I can put down what my area vectors point. And again, I'll draw what the electric field lines look like near the charge. Again, I need to figure out what the electric field looks like at each of these regions. So at surface A, I see that the electric field is going to point down. At position B, on either side, it's sort of going to point, down and to the left or down and to the right. And at position C, it's going to point down. So I see that my area and electric field are in the opposite directions. So the flux is going to be negative at the top, and it's going to be positive at the bottom. And it looks like the area and the electric field are sort of have a component pointed in the same direction here on surface B, so it's going to be positive. How do the magnitudes compare? Well, now I don't have the same symmetry where the charge is located for surface A and C. So surface A and C are the same magnitude and area, and the electric field is stronger at A than it is at C. So I expect this, so the flux at A, its magnitude to be greater than the flux at B. And that makes sense for the reasons I gave, but it also explains how surface B could be positive. Remember, the whole thing added together, there should be just as many field lines coming in as coming out. As you can see, every field line that enters A eventually passes back out, either through B or through C. So the net flux here is going to be 0. So the next thing we want to do is we want to think about how does this electric flux through closed surfaces compare to Gauss's law. Gauss's law tells us that the electric flux through a Gaussian surface is directly proportional to the net charge enclosed by that surface. So we want to figure out what is the net charge. If we go back to 1, we see that the net charge is 0. There's no charge enclosed. And we got that the net flux through the Gaussian surface was 0. Here we see that the net charge is -1 unit, negative Q naught. And we got that the net flux was negative. Here in question 3, we see that the net charge is 0, because plus Q minus Q is 0. And we got that the net flux was 0. And for number 4, we see that there is no net charge enclosed, no charge inside of the cylinder, and that we got the net flux was equal to 0. So our answers to the 4 previous questions are consistent with Gauss's law. Now again, if we look back at this question, we see that according to Gauss's law, that the net flux needs to be 0. And so if we know that through A, so in other words, what that means is the flux through A plus the flux through B plus the flux through C needs to equal 0. So if A is -10 and C is 2, then that means phi B needs to be 8 Newton meters squared per coulomb. So that when I add all 3 together, I get 0. Now we can figure out the net flux through each of the Gaussian surfaces below, but instead of drawing electric field lines and trying to calculate it, we can use a much simpler strategy of just adding up the net charge inside. So here I see that the net charge inside is 0. And so the flux is equal to 0 through this surface. Here I add together, I see that the Q enclosed is plus Q naught. Same thing here. And same thing here. All right, let's move on to 6. Now 6 hits at some very important aspects of Gauss's law. So I'm going to read through it. Here we have 3 spherical Gaussian surfaces, each enclosing a charge Q naught. Now in case C, there's also a -6 Q naught located on the outside. And here we have 3 students that are speaking with each other. Student 1 says, since each Gaussian surface encloses the same charge, the net flux through each must be the same. Student 2 says, Gauss's law doesn't apply here. The electric field at the Gaussian surface in case B is weaker than in case A because the surface is farther from the charge. Since the flux is proportional to the electric field strength, the flux must be smaller in case B. And student 3 says, I was comparing A and C. In C, the charge outside changes the field on the whole surface. The areas are the same, so the flux must be different. The question is, do you agree with any of these students? Now, if you look back to Gauss's law tells us First, it applies for any closed surface. So student 2 is wrong to say that Gauss's law doesn't apply here. As long as we have a closed surface, Gauss's law does apply. And it tells us that the net flux is equal to the charge enclosed. Notice Gauss's law says nothing about the shape of the Gaussian surface, how big it is, how small it is. All it cares about is the amount of charge that's enclosed. So the only student that I'd agree with is student 1. Since each Gaussian surface encloses the same charge, the net flux through each must be the same. Now again, I want to point something out here. Gauss's law doesn't say that the electric field doesn't change when you change the size of the Gaussian surface or you bring another charge nearby. It simply says that the net flux doesn't change. And net flux is that weird quantity we calculate by taking the electric field in the area, multiplying it across the whole surface, and adding it together. It's certainly true that the electric field on each of these equivalent points of the Gaussian surface is a different value. This negative 6q charge absolutely changes the electric field everywhere in this region of space. But if you do the calculation for Gauss's law, you will find that it does not affect the net flux. All right, next we have an application of Gauss's law. So here we have a large sheet of surface charge density sigma naught. And we're going to place a cylindrical Gaussian surface that encloses a circular portion of this sheet. Now, the first thing we want to figure out is, in terms of the surface charge density, what is the net charge enclosed by the Gaussian cylinder? So to remind you, a surface charge density is charge per unit area. So if I want to get the Q enclosed, I have to multiply the surface charge density by an area. So which area do we use? Well, the charge is located right here. And so that area is either A1 or A2, since they're equal to each other. So the Q enclosed is sigma naught times A1, or you could say sigma naught times A2, but not area 3. Remember, area 3 is the outside, the curved portion of the cylinder. So now I want to sketch the electric field lines on both sides of the sheet. I know it's a positive sheet, and so the electric field is going to point radially outwards from the sheet, like so. Now the Gaussian cylinder, it being there, doesn't affect the field lines, right? The Gaussian surface is imaginary. There's no charge on it. It's simply just a device we'll use to solve these problems. Now, the electric field at each point of the cylinder is, well, we're not quite sure yet if it depends on how far away we are on this distance L0. But we can certainly say by symmetry, there's no reason why the electric field at position 2 should be greater than or less than at position 1. So again, we might not know what the electric field is yet, but it's reasonable, again, by symmetry, to say that the magnitudes have to be equal to each other. Likewise, we know that the areas at the end of the Gaussian surface are equal to each other, because that's how we drew it. Now, if we want to figure out through which surface is there a net flux, again, we can explain it using a diagram. We see that the area vectors for the caps point parallel to the electric field. But the area vector for 3, no matter where you are on surface 3, is going to be perpendicular. And so A1 and A2 have non-zero flux, but A3, that flux is going to be 0. So now I can write the net electric flux through each of the surfaces and add them together. So it'd be A1 E1 plus A2 E2. And the reason why they're added together is because even though the electric field and areas are in opposite directions, when I figure out the flux, it's positive for both of them. And again, since the electric fields have to be equal in magnitude and the areas are equal, I can just write this as 2A E. Next, I'm going to set this equal to my Q enclosed, which was sigma naught A over epsilon naught equals 2A E. I see that there is an area, the same area on both sides of this equation, and so the electric field is equal to sigma naught over 2 epsilon naught. And so the electric field on the left end of the cylinder has the same magnitude, but for the right side it points to the right, and for the left side it points to the left. This question here, does the electric field near a large sheet of charge depend on the distance from the sheet? And if we look at our answers here, we see it doesn't, right? Nowhere did L naught appear in this answer. So we have a uniform field. All right, next we're going to apply a similar strategy to another Gaussian surface, this time straddling two sheets of sigma. So here, the net charge enclosed by the Gaussian cylinder, well, I have A times sigma naught plus 2 sigma naught times A. So my net charge is 3 sigma naught times A. Again, I'm just going to use A because A2 equals A1 equals A. Now, if I let EL and ER be the magnitudes of the electric field at the left and right end caps of the Gaussian cylinder respectively, the question is EL greater than, less than, or equal to ER? Now, again, the way I want to think of this is, how does the electric field look on either side of these sheets? So on the left side, the left sheet looks something like this. The right sheet looks something like this. Remember, it's uniform, but it does change direction when we cross over the sheet. So I see that on the left, I'd have the electric fields adding together. And on the right, I'd have them adding together. And since these don't change with distance, the electric field will be the same on either side. Will be same in magnitude. Right? Because it points away on both sides. So it points, in total, it points away. Now, on the inside, I don't have to worry about that electric field since the electric field on the inside only has to do with area 3. And we saw that that flux is going to be 0. So the net flux in terms of EL and ER would be A and then EL plus A ER. And we know that these electric fields are, are equal to each other, and so 2A ER. And if I use Gauss's law to find the electric field at distance L naught to the right of the rightmost sheet, and again, I can just use these two results, and I get that the electric field is equal to well, we'll do this. 2A electric field equals 3 sigma naught A over epsilon naught. And then I can solve for E. And I notice there's an A on both sides, so E is 3 sigma naught over 2 epsilon naught. And these results are consistent with what we'd obtained through superposition. Since if we're L naught to the right of 2 sigma naught sheet, then the electric fields just add together. So we'd have sigma over 2 epsilon naught plus a 2 sigma over 2 epsilon naught, and that would give us 3 sigma over 2 epsilon naught.